In this example, we're given a set, W, that's containing all of these 2 by 2 matrices such that A minus B equals C, so the difference between these two entries equals C here, and D equals negative A. So we've got a subset of the collection of all 2 by 2 matrices. So it's M 2 by 2, but with this specific 2 by 2 matrices that satisfy these two equations. Okay, so that's the subset that we're talking about. And so first of all, it's been established in the notes that the collection of all 2 by 2 matrices is a vector space. It satisfies all 10 of those axioms. So we know here that we're dealing with a subset. If this is your M 2 by 2, collection of all 2 by 2 matrices, then in this problem we're dealing with a subset that happen to satisfy, like I said, these two equations where A minus B equals C and D equals negative A. So this is our set W. Since it's a subset of a known vector space, we don't have to go through all 10 properties. If we wanted to show that it was a subspace, we could just show that it satisfies the 3. Okay, but I'm getting away from the actual question that I put on here. So I'm happy for that little discussion that I went through there, but let's answer the specific question here. So find a set of vectors that span W. Okay. The way we could approach this is to take these equations. All right, if C is equal to A minus B, here, so if we let this A, B, C, D be some matrix in this set, then we know that, let's see, A, B, we know that C is equal to A minus B, and D is equal to negative A. If this matrix is some matrix that belongs to W, then we know that that must be true. So it's got to have this form, where A and B are any real numbers. Okay, well then what if we decompose this into a matrix involving just the A terms, like this, so just the A part of each component, plus, and then another matrix with just the B terms. So 0, B, negative B, 0. Notice that if we take the sum of these two matrices, we'll have A, B, A minus B, which is good, and negative A. So the same thing we started with. And then from here, we can factor out A and write this as A times this 2 by 2 matrix plus B times this 2 by 2 matrix. And again, we're saying if this is any matrix in W, then it can be written as some number times this matrix plus some number times this matrix. And notice that these two matrices individually do satisfy these two criteria. They do belong in W. Here, let me verify that. So A minus B, in this case, will be 1. That's good. And then D equals negative A. Yes, this is the opposite. This entry in the D position is the opposite of what's in the A position here. Check this matrix here. So A minus B would be negative 1. That's good. And then D is the opposite of A. Well, sure, if they're both 0, then that's 0. So here we have two elements of this set W where we can express just any element of W as a linear combination of these two matrices. So in other words, these two matrices will generate all of W. So W is equal to the span of this matrix and this matrix. And there's your answer. There's the matrices that span that set. Now, if you're hung up on the word vector, remember that in this section, the word vector refers to an element of a vector space. So it's not necessarily the column vector that you picture when you see that word. We're expanding it to mean something more generally, which is elements of a vector space, which is a set that satisfies all those axioms. So vectors in this case are elements of M2 by 2. And we have found our two vectors that span W. Now there was a second question here that said, what conclusion can we draw? Well, there is a theorem right above this example that says anytime you have a span of a collection of vectors belonging to a vector space, then that is automatically a subspace of that vector space. So this tells us that W is a subspace of M2 by 2. And the reason it's coming straight from that theorem that I posted right above this, but I mean, we could talk through it. So span is the set of all linear combinations. If we know we're dealing with a subset of a vector space, then we're supposed to check three things. Does it contain the zero vector? Well, the span will always contain the zero vector because we could just let A equals 0 and B equals 0 in this case. Just make all of your weights 0, and that's going to give you the zero vector. Is it closed under addition? Well, yes. I mean, by definition, the span is a collection of all sums and scalar multiples. I mean, that's what the set of all linear combinations refers to. So a span is automatically closed under addition and scalar multiplication, because that's what linear combinations are. And so it satisfies the three axioms, and so it is a subspace.